So hey, we did sections 5.1 through 5.7, so I got a crazy idea. Let's go on and do section 5.8, which is about various scientific applications of exponential and logarithmic functions. So we're going to do a couple of different things, uninhibited growth and uninhibited decay. So the first is like frequently used for bacterial population growth, where you kind of assume it can grow without running into any barriers for quite some time. Uninhibited decay is most common radioactive decay, including, for example, carbon dating is an application. Newton's law of cooling, and then logistic models is a sort of in-between of growth and decay. So you can imagine trying to plot a more realistic growth model of like a bacterial culture in a little dish. It will grow uninhibited until it starts running out of space, and then the growth rate starts slowing down, and a logistic model sort of accomplishes that. Okay, so uninhibited growth. If you start at time 0, you start with a sub 0, that is your initial amount, and k is a non-zero constant, then this equation here is an exponential curve. Notice that e is bigger than 1, so if k is positive, the curve looks like this. If k is positive, the amount is increasing over time, and it's uninhibited. It will keep going up and up and up forever, according to the model, which is a weakness of the model, because in real life, usually it can't do this, without running into some sort of physical limit. If k is negative, then this exponent is negative, and that's a reflection across the y-axis, and then you'll have a graph that decays like that. Okay, so let me clear out all these pen marks. The sum result is this model here represents either uninhibited growth when the coefficient k is positive, or uninhibited decay when it's negative, but it's really the same equation one way or the other. Just based on whether it's positive or negative isn't that big of a difference. Okay, so either it's going to grow and grow and grow if k is positive, or it decays if k is negative. So for example, suppose you are counting how many cells there are in a culture. And here is the function that tells you how many cells there are. Since it's growing, then k needs to be positive. So here's an example. Bacteria is growing according to the following model, 90 times e to the 0.06t. N is measured in grams, because it's a lot more convenient to weigh your culture than to try to count how many bacteria there are. So determine how much bacteria you start with, what the growth rate is, what the population after 7 days is, and how long will it take to reach 250 grams, and what is the doubling time. Fundamentally, the equation that we're using, by the way, this a of t is equal to a naught times e to the kt, looks an awful lot like p is equal to e to the rt, or sorry, a is equal to p times e to the rt, continuous compounded financial applications. It's really the same equation, it's just we're doing a different application, but the math hasn't changed. So how we do the problem doesn't really change. So to determine the initial amount of bacteria, for example, that's just how many bacteria do I have at time 0, just plug in 0. So if we plug in 0, we just get 90 grams. That's what the 90 out in front represents, how much I start with. Okay. Part B, I forget what the question was, sorry. What is the growth rate? Right, so for part B, we just need to compare n of t with our explicit formula to the sort of general one, where k is the growth rate. And since k is given to be 0.06, we have a growth rate of 6%. This doesn't necessarily mean 6% per month or whatever. It's just taking the role of this constant k, like the interest rate in the financial model. So to find the population after 7 days, we just have to plug in t equals 7, and we get 137 grams. How long does it take to reach 250? Well, then I know I want to end up with 250. Okay, and they divide both sides by 90 without giving you the first line, so let's write that in there. So we had n of t equals n sub 0 e to the kt. So we want to get out 250, and we know we started with 90. So by dividing this 90 across to both sides, that's where this is coming from. Okay, now if I take a log of both sides or convert it into a logarithmic expression either way and divide by 0.06, which is approximately 17, it's almost exact. Okay, so in 17 days, we'll have 250 grams of bacteria. Okay. Finally, what's the doubling time? Well, since we started with 90 grams, the doubling time will be when it reaches 180. So just set the other side equal to 180, divide by 90, end up with a 2 over there, take a natural log, divide by 0.06. Sorry, the slides are in kind of weird order. It's approximately 11.55 days. Okay, it's exactly the same sequence of steps we would have done if this was, I have $90 compounded continuously at 6%. What's the doubling time? It's just we're using bacteria instead of dollars, but the math has not changed. Okay, so let's do another example. A colony of bacteria grows according to uninhibited growth. N is the number of cells, T is the time in hours, mind you. Express N as a function of T. There are going to be several variables in here. But now suppose it doubles in 5 hours. Now find a nice explicit function. How long will it take to triple? And how long will it take to double again? Okay, so take a moment, try to work your way through this. All right. So here is our generic formula that represents uninhibited growth. That's really all we can do there. But now we know that it doubles in 5 hours. So whatever n sub 0 is, remember n sub 0 is our starting amount. So now we know that at 5 hours, I have twice the amount I started with. So using the formula n of 5 must be n naught times e to the 5 times k. We just replace n of 5 with 2n naught, cancel out the n naughts, take a natural log, and divide by 5. And end up with a growth rate of about 13.86%. But now we have a nice growth rate up there, 0.13863. So we've managed to solve for one particular growth rate. And this, sorry, shouldn't be a k, this should be a t. We just found the value of k. All right, so the time needed to triple would be how much time is needed for n of t to be 3n naught. So instead of an n of t, just replace your n of t, and again, this shouldn't be a k, this should be a t. Replace n of t with 3n naught. Well, divide out the n naughts, take a natural log, and divide. And now we have t is about 7.9 hours. So it'll only take about 8 hours to triple the size of your colony. It took 5 hours to double. It'll take about 8 hours to triple. Now the next part said how much time is required for it to double again. Since it doubles every 5 hours, if I want to know how much time it takes to quadruple, I just need to double and then double. In other words, I need to wait 5 hours and then 5 hours. You could solve this by saying whatever the quantity at that time is, it's 4 what I started with. So I'd get 4n naught is equal to n naught e to the kt. And remember, k was like 0.13 something or other. I don't remember. Cancel these out and then solve for t. And you should end up with t being exactly 10. Okay, so there's a couple applications of exponential functions to uninhibited growth. We'll come back and we'll do uninhibited decay and radioactive decay. It's really the same functions we've been using for financial models. It's just we're changing the word problems. I am hitting the stop recording button and it is not doing anything. Well, let me mute myself so that you don't hear me get angry at my computer.